This is section 9.1, Modeling with Differential Equations, Objective 2, which is to build a differential equation from a written description of a situation or phenomenon. When we're done, I'd like you to be able to write a word you find in these types of problems that represents a derivative. And can you think of any other words that might mean derivative? With example 1, in some situations, a population will grow at a rate proportional to the size of the current population. We want to model this situation as a differential equation. So what we do is we look for words that mean derivatives. Here it says a population will grow at a rate. So when we're growing at a rate, we're talking about the rate of change in the population. So this piece right here can be rewritten as the derivative of the population with respect to time. Now, proportional to, that means it is a constant multiple of the size of the current population, which would be p. If we look at example 2, we want to consider the motion of an object with mass m at the end of a vertical spring. Hooke's law states that if the spring is stretched or compressed x units from its natural length, then the spring will exert a force that is proportional to x and opposite in sign. We're going to use the fact that force equals mass times acceleration to write a differential equation representing this scenario. So what we see here is that the spring is going to exert a force, so we can say that the force is proportional to, that's a constant, times x and opposite in sign. Now looking at this equation, we can see that we have translated this force that's proportional, but we don't have any derivatives. So we're going to replace force with what we know it equals. The force is the mass times the acceleration. Well, we still don't have a differential equation, so we've got to think about the position and the acceleration. And let's recall that acceleration is actually the second derivative of the position. Now that we have this written, we have a differential equation of order 2. With example 3, we have psychologists who have determined that the rate at which a performance improves for an individual who is learning a new skill is again proportional to the difference between m, the maximum level of performance, and p, the individual's current level of performance. We want to write a differential equation that represents this scenario. So again, we're going to look for something that represents a derivative. And we see here that the rate at which the performance improves, so that will be a dp, where p is representing the performance with respect to time, is proportional to, so that means it equals a constant times the difference between m, the maximum level of performance, and p, the individual's current level of performance. So we will have the maximum minus the current level of performance. Here we have a differential equation that says the same thing as the words in example 3. Lastly, with some investment properties, the rate at which the value of a property is changing, so there again we've got a rate at which the value is changing. So we can say dv for the value, the rate at which the value is changing, is directly proportional to the ratio of the current property value. Oh, it looks like we have that. Property value is a p, not a v, so we'll change that v to a p, is proportional to the ratio of the current value and a, the average value of the neighborhood properties surrounding it. So here we have yet another differential equation that models the scenario.